Hello and welcome. I am Beth Mashesky, Assistant Research Scientist for Hazardous Waste and Pollutants at the Illinois Sustainable Technology Center, which is part of the Prairie Research Institute at the University of Illinois. As a land-grant institution, the University of Illinois has a responsibility to acknowledge the historical context in which it exists. In order to remind ourselves and our community, we begin this event with the following statement. We are currently on the lands of the Peoria, Kaskaskia, Piankashaw, Waya, Miami, Mascoutin, Odawa, Sauk, Muskogee, Kickapoo, Potawatomi, Ojibwe, and Chickasaw nations. It is necessary for us to acknowledge these Native nations and for us to work with them as we move forward as an institution. Over the next 150 years, we will be a vibrant community inclusive of all their differences, with Native peoples at the core of our efforts. This webinar and all of the Illinois Sustainable Technology Center's webinars are certified green events through the University of Illinois Institute for Sustainability, Energy, and Environment. To find out more about certified green events through U of I, please visit sustainability.illinois.edu. To find out more about the Illinois Sustainable Technology Center's webinars or to sign up for the event's email list, please visit istc.illinois.edu/events. So a few housekeeping items before we get started. Today's webinar is being recorded. The recording will be available for viewing online in about a week. I'll be sending an email out to everyone who registered for the webinar once it is available. Everyone will remain muted for the entire webinar. You can type in your questions at any time through the Zoom Q&A feature. You will be able to upvote questions that you like within the Zoom Q&A using the thumbs up button under the question. I will be reading the questions to the speaker at the end of the webinar. At that time, the most popular questions will be asked first, followed by the questions in the order that they were received. If you have technical difficulties, please send me a private chat message. So with that, I'm very pleased to welcome today's speaker, Mihri Ozkan. Mihri is a professor in the Electrical and Computer Engineering Department, is a cooperating faculty in the Materials Science and Engineering program and the Chemistry Department, and is selected as the Climate Action Champion and Change Maker Professor at the University of California, Riverside, or UCR. She is a fellow of the National Academy of Inventors and Frontier National Academy of Engineering, and is UCR's first and only female engineering faculty to receive these honors. Mihri's research is dedicated to green energy technology and sustainable systems. Recent achievements in her research group include developing unconventional solutions for lithium-ion battery technologies using sustainable materials and green chemistry with lower power processing, and transforming waste glass and plastic bottles, biomass, and natural resources such as sand and diatoms into high-grade battery electrodes. Mihri earned her graduate degrees at Stanford University and at the University of California, San Diego. She has over 300 publications, 33 granted and 15 active patents, and has earned 56 scientific honors and awards for her creative research. So Mihri, thank you for joining us, and the webinar is yours.
Welcome. Thank you very much for the kind invitation and also introduction. I really appreciate it. And I think coming close to the Earth Day in April, I think this is a quite meaningful presentation talking about the direct air capture technologies and how they can help to capture carbon dioxide from the atmosphere. And my today's focus is not going to be on the lithium-ion batteries and all, majority of my research is, but mainly we'll be focusing on the carbon capture. And so we'll be talking about the pillars of specifically direct air capture technologies for carbon dioxide. And I will go ahead and get started. So hopefully my slides will move. There we go. And by the way, one of my hobbies is making cartoons. So you will be seeing a bunch of my cartoons throughout my presentation as well. And the points that I am trying to make at the beginning of my presentation is that the lungs of the earth that is known as the Brazilian Amazon forest they tipped being carbon sink to carbon emitter because of the vast deforestation. And secondly, the things that we need to pay attention is Arctic ice melts with the global warming, and then so loss of ice at the same time brings the second problem, which is the solar light's absorption, and originally was reflected by the ice, and that means that more heat is being absorbed by Earth, and then that's also adding on the global warming. About 90% of the heat from our fossil fuels are absorbed in the ocean, and this is kind of a tipping point for the severe weather events as well, having a surface of the ocean being warmer than usual, which is around like 2 to 2.5 degrees centigrade. And also, additionally, 25% of carbon dioxide is absorbed by oceans, causing more acidification. And then many of the economies worldwide are basically based on the seafood and related sectors. And this is a tipping point for our world's economy as well. This particular cartoon I specifically prepared just to kind of summarize the important pillars for the direct air capture of carbon dioxide. On one side is the capture fans, and then on the right-hand side is showing the pillars, which I am going to talk about in detail. And in October, November timeframe in Glasgow, we had our 26th conference of the parties for the climate summit. And about 40 countries pledged to abandon coal. And Australia, United States, China, and India have declined this actually. And then they pledge more in the emissions reductions in methane. And then everyone pretty much was agreed to switch to renewables, solar and wind, which will dominate by 2050, and away from petrol, diesel, and going towards the electrical cars and cleaner fuel for the aircraft, and plant more trees, forestation and deforestation by 2030. And decarbonize industry, which is the capture emissions at the source, and remove carbon dioxide from the air, which is the direct air capture and the content of my presentation today. And then bringing about like $100 billion pledge by the rich countries to help South Africa and others to move away from the coal use. All this is to keep the global warming around 1.5 degrees C, which was agreed by the Paris Agreement by the end of the century. So first, I think we need to look into what are the top emitters, and then and this basically graph is summarizing this nicely. And China is the major green gas emissions. Actually, this number came close to 33% now. And the US is second, and India, European Union combination here, Indonesia, Russia, Brazil, and Japan are the major carbon dioxide emitters. And now the China, as you can see from the graph, emits more than next three countries combined. And it pretty much like brings to the conclusion that what China does or doesn't do will largely determine the failure or the success of the Paris Accord and global carbon dioxide emissions. And it is important to look into also per capita emissions, not per country. And if we look at the per capita, and here you see that the wealthy nations lead. Saudi Arabia, United States, Canada, Australia, Korea, Japan, and Europe. And it is interesting that even the European Union have been leaders in the movement toward renewable and clean energies, they have the highest per capita carbon emission rates in the world as well. So how can we face down unabated coal power? And of course, the solutions are there, the renewable sources. And one of them is the solar PV and onshore wind. And now they are actually becoming cheaper and comparable to the coal power. And it's around like $50 per megawatt hour to $44 per megawatt hour, and in comparison to coal, it's pretty decent. And what is expected is that the renewable sources, wind and solar, are doubling actually globally every 5.5 years within the last 15 years, which is a great trend that we would like to see. And this means, in short, that 50% of the electricity could be coming from solar and the wind by 2030. And the main driver is the cost here. And the graph is actually showing here over the years how, onshore wind, offshore wind, and the solar cost is going down. And also at the same time, the battery storage, which is needed for smart grid applications, is also going down. So these are the main drivers to see this picture. And if you look into our innovation box to improve this even further, for example, in the solar area, perovskite solar cells are quite promising, and today it's been recorded that 28% efficiency demonstrated. And what is needed in this area that people may like to choose to work, the full encapsulation of devices and protect them from the external degradation from ambient moisture and UV. In the wind area, the simulators for wind farms and modeling, better control tools, I think can really increase the efficiency about 4 to 5%. And people can look into turbine controls to help this. And grid interface, we need today a better controllable grid interface systems to minimize the disturbances on the electric power system. And I want to kind of like give a baseline, where we are at today in 2021. If you look at the 2021, the global carbon dioxide emissions actually rebounded almost close to 5% in 2021, reaching to about 35 billion tons. So the increase in carbon dioxide emission over about 2 billion, this is the highest in the history. And the coal power accounted for about 40% of the overall growth in the global carbon dioxide emissions in year 2021, and reaching all-time high, which is about 15 billion tons. And another largest rebound occurred in the aviation sector. People started, after the COVID, people started traveling more, and that gave about like 22% boost in the carbon emissions, which is bringing and adding another 115 million tons. So what are the reasons for all this increase in the carbon dioxide emissions in 2021? And mainly is the record high natural gas prices, and people want to go back to the cheaper version, which is the coal. And so that's unfortunately one of the reasons that the closed coal basically plants are turned on back again. And another one is driven by China, and because they increased about 750 million tons between 2019 to 2021. And that's mainly because of the major economy experiencing an economic growth in China, both in 2020 and 2021. And only in 2021, China's carbon dioxide emissions rose about almost like 12 billion tons, which is coming close to, as I mentioned earlier, 33% of the global total. So what are the sources of carbon dioxide? So those are the ones that we need to pay attention. And one of them is the ammonia on the left top, corn and ethanol plants. And their exhaust pipes gives about 80% or more carbon dioxide. And carbon capture at the source has cost you about $10 per ton. And another source is the steel industry, and then the exhaust gives between 15 to 80% carbon dioxide, and the capture cost is between $10 to $60 per ton. And another one is the flue gas from fossil fuel combustion in air and the natural gas-fired power plants. And about 15% is the emission of carbon dioxide you observed, and the capture of that costs you about 60%. And to collect all these carbon dioxide that is being emitted to the atmosphere, we can use direct air capture. And but since this is not at the source, we are collecting already emitted and deposited in the atmosphere. And so we are working with very low partial pressure of carbon dioxide, which is around 414 parts per million. And then, of course, this increases the cost of carbon capture from the atmosphere anywhere between $200 to $600 per ton of carbon dioxide. We can use other net, negative emission technologies, and they are listed here. All of these actually has probably better, if you look at the cost perspective, they are much cheaper as compared to the direct air capture here. But they have also some limitations. For example, the coastal blue carbon requires a coastal access, and reforestation or forest management and all requiring land from farming. And then there are some issues like challenges with the implementation of management practices, both in agricultural and the forest management. And in the case of the bio one here, that needs basically land again and taking away from food and the biodiversity. Towards the end of the 2021, I did publish a commentary about the direct air capture of carbon dioxide. It's being published in Meteorological Society's Energy and Sustainability. And there I summarize actually the status of the direct air capture and things to pay attention. And if you ask the question, why direct air capture of carbon dioxide? Because some of these industrial sectors that I discussed earlier, the cement, natural gas, and iron and steel, and they are actually difficult to decarbonize. And there are also distributed emissions from the aviation and the transportation that also needs to be offset. And then we need to offset also emissions from wildfires, which start occurring more due to global warming. So direct air capture can help at this point. And industry today produces about 8 billion tons of carbon dioxide, and mainly, about the 70% of that is coming from this difficult to decarbonize industry that, as I mentioned. And even when you try to do carbonization at the source, decarbonization at the source, about 2 billion tons of the carbon dioxide emissions cannot be avoided, which requires other types of carbon capture technologies, such as direct air capture. And just within this month, and I also we publish, it's going to be available in April 15th. It's already online, available online in iScience. We discuss about the current status and the pillars of the direct air capture technologies, which I am going to talk about in details today. And let's look at the, how direct air capture works in short. And there are two main technologies. One is called like a liquid technology, and the other one is the solid technology. And both requires fans to run the ambient air through and push that air to the sorbent, the contactor. And in one technique, the sorbent is liquid, and then after the interaction, it absorbs specifically the carbon dioxide, and that captured carbon dioxide is separated with the regeneration step, and the sorbents is recycled back, and then the carbon dioxide moved to the storage. The similar thing with the solid technique is, in this case, the contactor has solid particles that are specifically absorbs the carbon dioxide from the air. Today, there are two major companies that are leading this effort, and one of them is the Carbon Engineering. They are based on the liquid technology, and they already have a pilot operational plant in Canada, started in 2015. And today they are working on a larger capacity. So these are showing the ton carbon dioxide, a larger capacity in Texas basin here in US, and using again their liquid technology. And here they are using potassium hydroxide and then precipitating the carbon dioxide coming from the air, and then it puts into the pellet form calcium carbonate, and everything is being recycled back again, all the captured liquid. The second major company is the Climeworks. They have today actually more than 14 now available and operational plants, and all the way starting from 2015 until today. And they are also trying to increase their capacity. They have in Iceland, Switzerland, Europe, and then even now trying to do it in US more also. And again, in the form of, as you can see, like membranes, the solid capture technique, and capturing the carbon dioxide and then storing. If you look at the DAC projects around the globe, so this is a nice graph that we also used and published in our review in iScience. And here, anything you have seen is a circular representing the direct air capture facilities. And the green ones are the operational DAC today. And then the red ones are the ones that are under construction. And the other technique is the carbon capture storage at the source, which is represented by triangular. And the green ones are operational ones again. And then the red ones are demonstrating the under the construction. So you see some number in China, India, and in Europe, in Saudi Arabia, and also in Canada and US. Again, published in January 2022, we discussed about the main players, which are the capture technology and what type of capture technologies are being used today and also being worked in research and development for carbon capture, not only in the DAC, but also at the source. And the liquid, membranes, MOFs, and solids are some of the classes of these capture materials that we have discussed in this paper in detail. So I want to go over some of the major ones here, and one of them is, like, of course, the liquids and the solid sorbents, MOFs, and also the membranes. And I will be talking and giving some examples of these. There's pros and cons and the cost related information. And alkali metal solutions, for example, and they are good sorbents, effective for DAC, direct air capture, and also they can be produced, in low cost. But some of the issues are the high temperature requirement for the regeneration step, which increases the operational cost. And another class is the organic amine solutions, and they are also effective for direct air capture. And here the problem is making the basically the sorbent is expensive, but operation is less expensive as compared to the alkali metal solutions. And ionic liquids, they are new emerging sorbents, and the main problem today is the cost, making the material cost and also the operation cost. Alkali and alkali earth metal powders, and they are also effective for direct air capture, and but they require high temperature again for the regeneration step. Even though the making them is inexpensive, again, the operational cost is high. Activated carbons, they are quite cheap, inexpensive, and also the operational cost is low, but there are issues with the absorption capacities, especially at low pressure, which is, direct air capture is at the low pressure, and so that's going to be a problem. And graphene-based nanomaterials, they provide high surface area for the interaction and capture of carbon dioxide. Of course, the scaling here is a problem, and also the synthesis today is costly, even though the operational cost is not as much. And solid amines and polymer salts are also other classes here, and their both material cost and operational cost are in the mid-level, and people are still working on these to improve the high surface area forms. The silicates, and they are chemosorbents with the potential to mass produced, which is great, and they are inexpensive. And today they are trying to provide, composites, and which actually they have higher thermal regeneration temperature requirements. So that's why the operational cost is in the mid to high level. Zeolites is another class of carbon capture materials, and aluminosilicate materials are effective for direct air capture applications. And the one of the problems here, it's the humidity in the environment where it's humid, since they also capture water, so it will compete with the capture of the humidity and the carbon dioxide. So this is a problem to solve, and they are both operational, and also the material costs are in the mid to high. MOFs is a next generation and quite promising material system that can be tailored specifically for carbon dioxide capture. But today the material cost is high and the operational cost is also high. And membranes for the modularity of the system for scaling, I think, is also convenient. And they require low energy consumption, which is wonderful, which we are going to discuss more, but making them today is expensive. And other composites of other chemistries, putting them together, like membranes, MOFs, and so on and so forth. So that also kind of like adds into the material cost, which needs additional work. In summary, so we have mature technologies, next generation and early stage, and carbon engineering is using more mature technology, and the Climeworks is using more next generation technologies, which is great. And they all come with the pros and cons that I discussed in detail earlier, which is exciting for researchers such as ourselves. And we also looked into the scalability of direct air capture, and together with thought leaders in academia and industry, we discussed about the potential and feasibility of scalable direct air capture, whether the direct air capture is a sustainable technology. People such as, Carlos, he's the CEO of the Climeworks, and Marcia McNatt, she's the president of National Academy of Sciences, myself, and Eda, she's the CEO of Carfix, and Kaliat, a member of the National Academy of Inventors, and Paul is the president of the National Academy of Inventors. Sochi and also Jennifer from the US Department of Energy, we did publish and discussed our personal opinion about the scalability of direct air capture in CAN Voices. And this graph actually shows the large-scale, widespread direct air capture or point source capture or carbon dioxide utilization and implementation in California. And this is the source is coming from the California Energy Commission and Guidehouse Incorporated. And what they have shown is that the financial feasibility is one of the, I think, number one, I would say, the challenges that direct air capture faces today in California. And then the scalability is another challenge. And besides that, technical feasibility and also environmental policy are some of the challenges that are being foreseen for the DAC specifically in California. In our review in iScience, we looked into the land requirements of direct air capture. If we were to, basically use the Climeworks or carbon engineering technology, one is again liquid, the other one is the solid, and to go back to the pre-industrial levels, how many of the plants we need, and so that's pretty much like we need about 2.4 million plants from the Climeworks and 9,980 plants of the carbon engineering. And if you put together the overall land requirements, so it's about 2.5 times both of them New York. So if you use 2.5 times of New York land size, it will take care of the entire carbon dioxide problems that we have today. And if it's at one point you may think that this is like a lot of land, but actually the land requirements for DAC plant, if you deploy, it's about 0.2 kilometers square per million tons of carbon dioxide removable. And if you want to compare this with the reforestation, which is another negative emission technology, it requires 862 kilometers square per million tons of carbon dioxide removal. So it's much, much less compared to the reforestation. And of course, DAX cost is the major and big, I guess, the elephant challenge, if you like, that people are working very hard on this. And so I summarized here the both capital cost and operational cost of different technologies. The top is showing the liquid sorbent, and the bottom is showing the solid sorbent. And if we compare the capital cost of the liquid sorbent technology of DAC versus the solid sorbent technology of DAC, the solid one requires higher capital cost. But if we look into the operational cost, because of the high temperature requirements, close to 900 degrees C versus 100 degrees C, and you need much more energy to run the liquid sorbent DAC, so that's why the operational cost is much higher. And it has been shown here also which steps in the liquid sorbent and which steps in the solid sorbent actually are the energy consumers. And air contactor is common on both, so that's why you need that regardless. But in the liquid, the calciner, which will be running 24/7 and the 900 degrees C. So this is one of the major energy thirsty step. And then the steam here in the solid sorbent one is one of the energy thirsty steps. But if you can use some of the waste steam from, for example, other industries, then I think you can lower the cost here. And this is simply showing, again, the heat requirement and electricity requirement of the liquid technology versus the heat and the electricity requirement of the solid DAC. You can see in the numbers that the heat requirement for the liquid is much higher compared to the solid DAC, and also the electricity requirement is higher. And here I am discussing about if that electricity is coming from different energy sources, renewable sources like solar, nuclear, wind, natural gas, or geothermal, how that will reflect to the final cost. And as you can see, the solar with storage will cost the most. And then as compared to the geothermal, if you run on the geothermal, the DAC plant is going to be about 42% less expensive than the solar power. We also looked into detail about the environmental impacts of direct air capture. And so as you can see, looking at the particulate matter, and toxification, human toxicity, or environmental toxicity, and issues with the freshwater or the marine life and all. And one of the, I think, few items that to pay attention is the freshwater exotoxicity, land use, water scarcity, and the resource depletion for the energy. So these are the highest impact, negative impact, I would say, for DAC. But we said that the land use is much better compared to like reforestation or others. And another points we need to pay attention is the water, and it requires about 7 to 13 tons of water per ton of carbon dioxide. In the areas where water could be a problem, then this is something to consider. So in summary, in our review, so we thought that these are the major key players and the pillars of the direct air capture. Of course, the type of the capture technologies that I mentioned will impact, and the choices of the energy sources, and then how we can reduce the energy demand, and which definitely defines the final cost, both operational and also the capital cost, the environmental impacts, and also political support. Till now, I didn't talk about the political support, which I would like to mention in the next few slides. So political support is certainly one of the enabling pillars of the DAC, and is highly critical to drop down the cost of DAC below to $100 per ton of carbon dioxide. And early stage investments and supporting policy frameworks are necessary to implement mass manufacturing and deployment of DAC. And in US, Department of Energy now invested about $24 million to advance the transformational air pollution capture in March 2021. And federal section 45Q, which is an incentive, offers about $20 per metric ton for saline and other forms of geological carbon dioxide storage, and about $10 per metric ton of carbon dioxide stored geologically through the enhanced oil recovery. At the climate summit in April, China made a pledge to achieve net zero carbon emissions by 2060, but we really need to see this happening. The UK planned to invest about 70 million pounds in DAC, and Climeworks in Europe received about 50 million euros in total from the investors for commercialization of DAC, and then people are also trying to support this, improve the tax benefits in South Africa. So in US, here is the situation, and this basically the government, the administration, they are trying to give 240 million for negative emission technologies and improving the nuclear, fossil fuel, renewable energy, and so on. And about like 61% increase in spending of Department of Energy on carbon capture, use, and storage has been observed. And this administration also trying to launch a 50-50 cost sharing initiative to deploy first wave of carbon capture facilities in the United States. In April, myself and Radu Kastelsian from the Oak Ridge National Labs, we guest editors of this special issue that we discuss about the materials for carbon capture technologies. And we also have a basically introductory article in this issue. At the same time, a number of great authors discussed and reviewed like different forms of different types of carbon capture materials. So I encourage you to look into this also soon. And one thing is that the cover, we prepared the cover for this issue, and the background picture was taken by Radu from Alaska. And I organize and draw and arrange the final cover myself. So I want to give you a prospect for the future, what's waiting for DAC. And the point source carbon capture won't be enough. So that's the given. And about 2 to 10% of the carbon are still let go, even though if you have a point source carbon capture. So that's why we need an alternative carbon capture technologies, which is direct air capture. And so we simply point capture has to scale up from about 40 million ton per year today to 6.6 billion ton by 2050. And that has to grow from 3,000 metric tons per year to almost 1 billion ton by 2050. So this is based on the IEA's analysis. And if we try to build all those plans, 1 billion ton by 2050, this will cost about $655 billion to $1,280 billion over the next 3 decades. And this is depending on what type of technology you are using for capture. And to meet the global goals using DAC alone only, which you have to remove about 1,000 gigaton carbon dioxide by the end of the century. So we need about 13,000 DAC plants with 1 million ton carbon dioxide capacity. And today we have only very limited capacity, which is only about 19 operational DACs. So if you were to put 13,000 DAC plants with that capacity, high capacity, we need about 1.6 to 1.7 trillion capital investment. So moving forward, DAC is still in infancy, the technology. So what we need is we need to work on the contactors, sorbents, and regeneration, and mainly trying to reduce the cost of the sorbents and improve the sorbents, and at the same time, the energy requirement to run the contactors and the regeneration steps. So that's how we can make it economically viable to lower the cost below to $100 per ton of carbon dioxide. And there are quite a bit activities today, and many startup companies are actually trying to work on this. And again, this is a slide from the California Emission and Commission that is showing a number of companies, startup companies that are working on this area to improve using electro swing, moisture swing, and magnetic induction swing, metal organic frameworks, and so on are some of the active research areas that people are working today to lower the cost. And I just came to the end of the presentation, and what actually I would like you to look into the slide, which shows the humans are the tiny fraction of the weight of living things and have a disproportionately large impact on our environment. And the green shows the weight of the plants, which is around 450, which is the majority. And the bacteria is the second, weight, the highest weight. And the animals is around like 2 gigatons. And then if you look at the humans' weight total, it's 0.06 gigaton. So even though our weight of living is smallest, and we have a disproportionate, large impact on our environment, so we need to be mindful about what we are doing to our environment and care about Earth. And I know that at the back, Elizabeth, you keep looking at her watch and want me to finish so we can go to the next session. And I really would like to thank for the opportunity to give this presentation. And I would like to thank for the invitation and be ready for any questions you may have. Thank you.
Sure, thanks, Mihri. Very interesting presentation, and I love the doodles. Let's get started with our questions. The first one is, which projects, carbon capture and storage at the source or direct air capture, should get more funding or priority moving forward?
I think, in my opinion, so this is my, again, the personal opinion, I love to capture the carbon dioxide at the source. So if we can capture the carbon dioxide at the source, that's wonderful. But as I mentioned, not the 100% of that carbon dioxide is being captured. So there is still about 2 to 10 basically percent that is being released, unfortunately. And some of the sources that I mentioned, difficult to decarbonize, and also the aviation, transportation, and some of those are still need to be taken care of. The carbon dioxide need to be offset. And so at that point, I think DAC could be coming to the picture.
The next one is, how did you calculate to compare the cost of materials in operation? Also, you show the cost of captured CO2 is $200 to $600 per metric ton. Could you provide a reference or basis for the estimate range? Recently, the cost of direct air capture of newly installed in Iceland is about $1,200 per metric ton.
Yeah, so if you, it's detailed, so that's why what I will do is I will refer you to our publication, which also gives the main source if you are going to look into this one. So please go and look at our publication in iScience, which talks about in details, you know, where the sources and then each number is taken. It's simply based on one particular operational DAC plant. And of course, the case-by-case operations needs to be different. For example, as I shown here, that if the DAC is running on geothermal, using geothermal power versus solar and all that, which will impact the final operational cost. And I would recommend you to look into all these the sources that I listed in my presentation to get the true the source of where these numbers coming
from. You may have already answered this one, but if you could elaborate a little more. Which CO2 capture route could be practical in the future upon your experience and knowledge among many developed or will be developed methods?
Yeah, again, I think carbon capture at the source, the point source capture is, I think, the way to go. And there are some mature carbon dioxide capture materials available for this. But there are some that are like a next generation one. And why people are working on the next generation one? Because they would like to increase the capacity of the capture of carbon dioxide, and they are trying to improve the stability of this sorbents so that they can recycle many times. And also production, the making the sorbent, they try to make as such that the requirement for the power will be less, and at the same time they will be cheap. So it will be coming from renewable sources or cheaper sources. So those are, you know, some of the points that people trying to embed into the better next generation approaches.
What about the membrane technology makes it expensive to manufacture? Is it expensive due to the scarcity of resource that is needed to make them?
Actually, the membrane technology is quite promising, and even though it is today, it is quite expensive because of the modularity and then you know, how to lower the maybe even the cost of, you know, if you don't think about the cost of the membranes, the plant, the DAC plant, I think the membrane is probably the way to go. So again, for the modularity of the implementation of these plants, I think the membranes are important. This is a very active area of research. As I mentioned, people are trying to look into the composites of membrane and membrane technology embedded with MOFs, method organic frameworks into the system, just to make it more specific to increase the carbon dioxide capacity and durability and so on. So it is very active research area today.
You listed monoethanolamine as the liquid sorbent. There are more efficient advanced sorbents for point source capture. Are they being considered for better direct air capture?
Probably, you know, some startups are doing it, but the problem is with the liquid that people actually kind of like tending to try away, you know, going away from it because of the regeneration step. It's a requirement of very high temperature for regeneration steps. As I mentioned, in this case, it's the about 900 degrees C. And that's the more energy demanding step that adds on to the operational cost.
How will direct air capture locations be limited by availability to sequestration locations or access to those locations?
Yeah, I think this is a good question. And again, the requirement for water is one. So you don't need actually arable land. It can be like the top of the mountain and so on and so forth. But of course, the accessibility to water and the energy. So there has to be a supporting renewable, you know, plant, either solar, nuclear, wind, or geothermal source of power next to it. So that's one of the, I think, requirements. And at the same time, when you collect and store the carbon dioxide and you want to ship this carbon dioxide to a port or the ground transportation and so on. So you want to minimize that as well. Otherwise, if you look at the life cycle analysis overall to entire system for DAC, then it may not be negative emission otherwise, because if you basically produce more carbon dioxide by transportation of the carbon dioxide you captured, doesn't make sense.
Membranes are usually bulk removal. With such a small driving force, how will membranes be competitive?
Yeah, so I will actually refer you because it is involved, and because of the shortage of time, and I will let's see, where is the yeah, so here we talk in detail about the membranes, and then we have actually quite promising ones from Japan, and like a number of researchers are working on this from Japan and developing the membranes for both direct air capture and other forms of carbon capture. So they have also proposed modular systems where a number of membranes can be added, and then carbon dioxide is passed through and then, you know, circulated many times. So each passes will give you a more carbon dioxide capture opportunity. So again, there are lots of factors in the membranes, and there are like some composite membranes, as I mentioned, with MOFs and other chemistries, amines, and so on. And please go and look into our publication in journal Chem.
That was the last question that was asked online. So what final thoughts would you like to leave us with?
Yeah, again, like going back to the slide that I try to emphasize, really we have a disproportionately large impact on our environment. So we need to be mindful that and take the responsibility for the rest of the living things on Earth. So it's all in the mercy of what we do or what we don't do. So that's why just being mindful is important. Thank you.
Great, thank you for a wonderful presentation. And thank you to our audience for attending, and we'll officially close the webinar now.